Thank, thank you for the invite. I'm super excited to be here. So we have a packed agenda. Let me bring the slides and we can kick it off. And click the share. Okay, can you see my screen? Yeah, perfect. All right. So we're going to talk today about, I assume you are here because you want to learn about forecasting. And we're going to talk specifically about forecasting with linear regression model. Um, a little bit about myself. I'm a senior manager at Apple, and that's my day-to-day work. Um, in this talk, I'm not representing Apple. I'm active in the both R and Python community. I'm doing a lot of stuff about the time series and MLOps. So that's why also you see here the Docker Captain. But originally, I started as a time series person, so I'm really excited to. It's been a while since I did some workshop about forecasting, and I'm super excited about this topic. Um, if you like, I have a newsletter about data science that I write weekly about updates. You can find it on my LinkedIn profile or in Substack. Um, and I think this is also should be uh, connecting to this. All right, so we have a packed agenda for today. Um, we start by we're going through some slight theoretical background, which is like 3.5 slides, really short. I want to keep it short and do more hands-on. And then we go to R, VS Code. I'm using VS Code, but if you want to follow along, you can use it either your preferred IDE, Positron, RStudio, or VS Code. We'll show you a little bit about the settings if you want to run the code along with me. Um, Everything will be available. Um, so you can, uh, if you're not able to set the environment, stay, listen. I have all the code available in Quarto doc. You can go and reproduce it after the workshop. So don't stress if you cannot really install now the dependencies or everything. Everything will be available on GitHub, and you can clone it, fork it, and reproduce it. And so we're going to start by talking about the prerequisite for forecasting. Forecasting with linear regression require a lot of feature engineering. And those features are, you need to understand the descriptive process of time series. So we're going to talk about simple tools for analyzing time series that we will leverage to um, understand what type of features we want to build, such as time series decomposition, correlation analysis, and seasonality. I plan to spend no more than 45 minutes. We have 2 hours, so I don't want to spend more than 45 minutes on those topics. And then we go to forecasting. So everything we'll do today, try to do it from scratch. So instead of using a built-in functions, we will build the features for modeling trends, seasonality, and building probabilistic forecast. We will, whenever it's applicable, we will build it from scratch. And the goal is just to intuitively to understand how the mechanism of the forecasting is working. Obviously, in real life, you probably should go and find a package that give you this functionality, but when I found it as a good practice to learning, as a learning practice is to just build, build it and play with it, that you will understand how the mechanism of this process is working. We are a small group, so anytime if you have questions, feel free to pause and ask. Happy to answer. If I see there are too many questions, I will just tell you to pause and we will have breaks to answer those questions. But feel free to interact. And I cannot see the chat, so just um, you can unmute yourself and ask any question. Maybe we start with a short poll. Uh, how familiar are you with linear regression and with forecasting? And I guess I need to go to the chat to see the answer. Uh, let's see. How do I see the chat? Okay. So I assume that you have some basic knowledge about linear regression and forecasting. I assume that you don't. Or understand what is forecasting, but um, you did not do any forecasting. If you are, I see there are people who are familiar, um, so we can really go faster on some of the topics. Great. Um, let's go back to the slides. Thank you for the answers. Okay, all the materials are available in this repository, and I will send you the link on the chat in a few seconds after the slide, so bear with me for a few more seconds. All right, let's talk about time series modeling approaches. We're going to focus today on linear regression, but there are many approaches for forecasting. There is the classical statistical models such as ARIMA, Alt-Winter, smoothing methods, and so on, state space models. And those models are very old but effective models. They are very powerful when you have a structured time series data, uh, meaning that your patterns are very regulated, right? So if you think about the air passenger data sets, which is, very nicely academic time series, or if you're doing some electricity forecasting or this type of that the demand signal is very clear. Those models are very powerful. They're simple. They are easy to compute, but their limitation is when you have unstructured events such as outliers, and seasonal, non-seasonal recurring events, and so on, or a structural break, like the COVID effect that shift a lot of the time series that people regularly usually worked with. And so um, in this case, you want to go to regression. So linear regression is a very powerful model. It's simple, easy to use, and you can build features. Um, and then there are other type of regression. There are Bayesian models, there are machine learning models, and deep learning models, and recently there are foundation models for time series. So if you're familiar with Nixla, they have the time GPT, Amazon, they have their own Chrono, I think it's the name of the model. Google has a also a foundation model and so on. So those models are like a language model that are pre-trained with a large amount of time series, and they should be familiar with a lot of uh, forms of time series, and you can take your own time series and feed it, and it should uh, forecast it, but it's a black box. So I think if you're looking at all those categories, the difference between the classical and the rest is the linear regression is somewhere in the middle. It's the bridge between the models that are only used historical and regression models. And the foundation model is a different class. Um, it's a transfer learning approach. But if you understand how linear regression works with time series, you can easily apply it with Bayesian, machine learning models like XGBoost, or advanced regression like GAM, GLM, and so on, and deep learning models. So we are going to focus on this, and hopefully the takeaway that you can take from this workshop is that you can apply it to any other regression model. So why we are using today linear regression. So the simple answer is it's very intuitive to use linear regression, especially for learning purposes. It's on really smooth. You don't need much of compute to, you need a fraction of CPU to calculate a regression, to train a model. No need for tunings. There are no tunings parameters. It's robust. You have the interpretability, and we can focus on the features and how the features working rather on starting to tune the models. There are also limitations for regression, like scalability, if you have many features or feature selections. But for the scope of today, we will just focus on the features itself. And since we are going to use linear regression, so if you took a basic stats class, there are the core model assumptions about um, linear regression. The first and foremost is the linearity of the coefficient. And this is the big myth about linear regression, is that a linear regression can only handle linear lines and because of the name, but the truth is that linear regression can handle non-linear data. The linearity is referred to the coefficient. The coefficient must be linear, so it's a linear combination, but you can apply it, the variables or the features can be non-linear. So technically, and we're going to do it today, we're going to model non-linear data and see how easily you can do it with linear regression. The error should be independent, and the fitted value, like the error should be also distribute evenly. This is the almost cadasticity assumption. The residuals should be distributed normally. And this is mainly if you are building a prediction intervals or you want to use the error terms of the residuals, they should distribute normally. And no perfect multicollinearities mean that the variables that they're using should not be correlated. Now, the last assumption, we when you're using time series, we typically lose this assumption and we probably will violate uh, the assumption, mainly because think about the nature of time series. If you are using legs input in your model, you can assume that if you use, let's say, your regressio model against leg 1 and leg 7, you can assume that there is some correlation between leg 1 and leg 7. So this is obviously you cannot have perfect multicollinearity because mathematically you cannot um, generate a regression, but you are violate the multicollinearity assumption, and that's the assumption that in time series we a little bit lose this assumption. And the process of forecasting, and this is the last slide before we go to the notebook, so bear with me. Uh, we usually start with the raw data. We then build the features. We then train a model. We score the models. We will do some evaluation process. But there are different techniques like splitting to training and testing or using back testing, which is a more robust method. And then we select the model that perform best and generate the forecast. On today's workshops, we will strictly focus on the features and the model evaluation, less about the model scoring. Um, so the fact that I'm not talking about the model scoring because we can spend 2 hours about model evaluation, and I want to focus on the feature engineering. So um, I don't want that you the takeaway from this workshop that you need to skip it. No, but I just want you uh, know that also you need to do model evaluation. But today we will mainly focus on um, the feature engineering. So with that, there are any questions before we go to the settings. Okay, so maybe I will share the link of the repo on the chat. And so this is the repository. Feel free to fork it. If you want to follow along, you can um, fork it and clone it to your local um, environment. And there is also this link that lead you for the rendered version of this workshop. So all the notebooks rendered versions are available here. So for example, um, if you go over here, you can see that this is the seasonality that we're going to go over. It's already rendered. And if you want, you can read it after or while we are demoing those concepts. So this is available. If you want to so for setting the environment, there are a few options. And there are instructions on the README, but I will go quickly. I'm using VS Code with Docker using the dev container, and I assume that that's a rare method to run R. So I also created a renv setting. So you have this renv.lock with the environment, and you just need to, if you're using renv, and there are instructions here, you need to go and do renv restore, and it will set the required libraries for this to run this workshop. If you're using Docker, you simply go click on this button over here and um, do reopen the folder in container. It's already open in a container, so you just need to okay, do it there. To just demo it, you go over here and reopen in container. And if it's the first time, when the first time you're running it, it will take a few seconds to download the image, but after that, you can see that it is um, open fast. So that's the repo. Let's go quickly over the repo, and I will maybe increase the font that you will be easy to read. Okay. And so we have seven notebook. The first one is the data. So I already downloaded the data. Quickly to talk about the data, we start there and then we can move to the rest. The data, and let's go over here, over here. So the data that we're going to use today is from the EIA API. The EIA is the US Energy Information Administration. It's a great resource for time series data. This website is under the Bureau of Statistics, the US Bureau of Statistics, and it provides more than 1 million time series. Some of them are live time series, so you can really, if you want to find like a good time series to practice, build tutorials, and so on, this is really a good place to start with. I use the API to download for this workshop 3 time series. We're only going to use two of them, but the first one is the number of natural gas consumers in California. So this is example for a non-seasonal time series. And the second one is the US monthly demand for natural gas. And this is, you can see a more nice seasonal time series. So those are the two series that we're going to focus on this workshop. There is a third one that I didn't use, but the example for hourly time series data that is available. And this time series is get updated daily. right? So if you have a daily data time series in this and you want to build API on automation and play with it, it's a really great resource. So those are the two time series that we're going to use. The other the other notebooks are for each topic there is a dedicated workshop, a dedicated notebook. There is a decomposition is the second one. The third one is about correlation analysis. The fourth one is about seasonal analysis, and and there is for trend, seasonality, and the last one is about probabilistic forecasting. Okay. And so let's jump to the decomposition. And maybe I will render it while we are. So decomposition, I assume that most of you know what it is, but I will just make sure if there are people that knew for time series. Decomposition is a common method to break the time series into the core components, which is the trend, the seasonal component, and the irregular, where the irregular is represent any patterns in the series that cannot be explained by the trend and the seasonal component. And it's very powerful tool because it's enable you to understand what are the underlying patterns in the data. And so if you use um, the stats library, you have the decomposition function that is built in the stats library that give you this functionality. And then there is uh, a more modern methods from the uh, fastest library by Professor Rubinman that provided to teachable objects. We're going to use today teachable objects, and the reason that it's more easy to work with as it is a data frame and not a TS object. For those who work with the TS objects, those are very horrible or not convenient to work. So there are mainly two methods to decomposition: classical decomposition and STL decomposition. The classical, we'll see now the classical is working. So we load the first data sets, and the data sets are available on the data folder. So you have a TS R data object, and if you can load it using the load method, and we'll look at the natural gas demand for natural gas in the US series, and you know you can see that there's as nice seasonality, and it's trending. Now, the goal of using the composition is to understand better the trend and the seasonal component. But also you can learn more about outliers. And so we start with a classical decomposition, and then we move to the STL and understand the difference between the two. Classical decomposition is a very simplistic method. It starts by smoothing the series. So we take the series and we calculate the trend by using a moving average. So for example, for each point, we'll calculate the moving average with for example, this is the 12 months frequency, the series. So we'll take for this point, the previous 6 point and the future 6 points and calculate average. And this is when you are applying it to all the points, you get a smooth line, right? So this is how for point T, we'll take the sequence of the previous points and the 5 points and the next 6 points, and then divide it by 12, and you get a smooth curve. So if you go over here, you can see this is the trend that we are receiving after removing the seasonality by using smoothing method. Once we calculate this, we are subtracting from the series the trend, and then we get the uh, seasonal adjusted. And from this, the next step is to calculate once we did trend the series, is to estimate the seasonal component. So we are taking the D-trend series and we calculate for each frequency unit the average. So for example, you can see here we got January, it's equal to 765,000 units. And this is essentially, it's once we did trend, we take all the Januaries and calculate the average of all the Januaries. So that's why every January will be the same because it's average across all the Januaries that we have in this data set. And similarly, we will do it for the other months, for February and so on. So that's how you calculate the seasonal component. Once we have the trend and the seasonal, we subtract it from the series and then we get the remainder or the irregular component. And technically, if we capture all the information with the seasonal and trend, we expect it to be a white noise. Sometimes we are not fortunate to have a nice seasonal and series with seasonal and trend, and you see there are some outlier here. We'll see how to handle it in a second. So this is very simplistic, give you the information. But the downside of this method is one that you see that if your series is very long, your January, this is 20 years ago, might be different from the January uh, in last year, right? So the seasonality change over time, and assuming that it's stayed constant it's a very strong assumption that not valid in most cases. This is where the STL decomposition is coming, which is using a regression on the backend to decompose the time series using a window function. So for example, here I'm using the STL method. I'm using it from the FastES library. And I'm setting my window for the trend and for the seasonal component. And I define, for example, how many seasons, here it's 7, so like it's a 7 years window to calculate the seasonality. So over time, it's a window that move and always calculate the last 7 years seasonality. So this is more flexible and enable us to capture changes in the seasonality. So if we plot it, you see that a seasonality is changing, and if you see January 2025 is different than January 2011, right? And so that's the effect of the window. And part of it is also the calculation of the trend is taking into effect. So you see that it's not that our January drop over the years is more our effect of the trend is stronger than the change in in seasonality. But I like this method, and we're going to use this method today. So you have here the code to plot it. I like to use Plotly, and the reason that it's more flexible and able you to zoom and track the built-in functionality of the Fibble or Tibble libraries are based on ggplot, which is nice, but it doesn't give you the interactivity. So I will use today Plotly for the reason of the ability to the interactivity. And to avoid repeating it, we're going to use this plot a lot, so I created a built-in function that we'll use today. Let's pause for a second and talk about the irregular component. When you are analyzing data, the irregular component could be a gold mine of information. Um, so what I like to do usually is to add standard deviation. So I want to take the the irregular component, calculate the standard deviation, and add lines of um, 2 and 3 standard deviation in absolute value. What does it mean? You can see here, I after I calculate, I add those 2 lines. What those lines give us? Give you a range. It's just give you an ability to flag points that you can consider as suspicious outliers. Um, and I decide randomly or not randomly. It's like that's what I think makes sense to segment it between 2 to 3 standard deviation as the orange range, and above 3 standard deviation as red. And I map those points to the series. So when you are starting to work and with the time series and you're trying to think about features, this is a useful plot because it gives you the points like, oh, what happened here? This is higher than usual. Could it be there was some high demand because the weather during this year was higher than the usual? Or maybe that was like a change in the regulatory or something else. So it keeps you focused on where you want to spend the time on investigate rather than trying to go doing a lot of iteration until you get to those anomalies. Now, not always a point that flagged by this method is anomaly. It's a model and it's estimation. It's estimate of the trend and seasonality, but it's not the real seasonality or the real trend, right? So that's always need to know that it could be also a regular point, or we are missing some of the outliers. But in most cases, it really highlight the points that you want to look at and think about features. And one more thing is that the functions here, I created a set of functions to support this workshop. And along the workshop, we're going to use um, this file to load to source those functions. One of the functions is the plot decomposition that give you this functionality. So instead of repeat all this long code, we were going to use it. Any questions so far? Okay. Let's go to the next topic, which is correlation. So correlation is then after you usually the first thing you do when you are analyzing a time series is look at the decomposition, and the next thing is the correlation. And the reason correlation in time series is go side by side. And a way to think about it, most time series, unless it's a random white noise, has correlation. So if you think about the temperature, for example, temperature now is highly correlated with the temperature in the last hour. And it's going to be very correlated with the next hour temperature. So this relationship, you are carrying information from the previous observation, um, is very strong in time series. And we typically use the autocorrelation function or the ACF to calculate and plot the correlation in time series and enable you to understand the nature of the patterns in the series. So again, we're going to use the same set of libraries. Since we are going to work with the Sybil object, we're going to use the tools from the FastTS and the Fibel tools library to calculate some statistics. In this case, it's the ACF function. So we're going now to focus on this time series. This is the number of consumers of natural gas in California. And you can see that something happened here, and the first year is probably like is not relevant. Maybe they started to collect or to launch this series and there is some missing information. So we're going to cut this year and focus from, in this case, anything that's above 1986. So now you get a nice time series. You can eyeball it and you can see that it's just a trend. There's no, at least visible for the eyes, seasonality. And we will start by checking the correlation. And using the ACF function, you get the calculation. And to explain what ACF it does, it's take the series and start to calculate the correlation of the series with the corresponding legs of the series. So you can see here that this is the correlation of the series with the first leg, and this is the correlation of the series with the second leg, and so on. And the idea is that we want to see what legs are highly correlated with the series. So I'm taking the series, and again, I'm plotting it with Plotly, and I'm calculating the prediction intervals or the confidence intervals for this calculation, and I'm getting this plot. So let's expand this plot. So the first leg here is the correlation of the series with leg one of the series, and the second is the correlation of the series with the second, and so on. The range of the correlation could be between 1 to -1, where 1 is positively correlated and -1 is perfectly negatively correlated, right? So if it's 1, the series is moving with the same exact direction as the leg is impact the series in the same 1-to-1 correlation. And you can see that this is a typical correlation plot for a trended series. So you see that the first leg is highly correlated, and as you move further in the legs, the correlation is decaying until it's getting too close to 0. One thing to notice that this line represents the confidence intervals, and we usually assume that if the correlation is below this line, we can ignore it. It's equivalent that there is no correlation. So technically, in this case, we can say that the series correlated with the first 9 legs, and beyond this, there is no evidence for correlation. Again, like any model, it's estimation. So, it could be that maybe this very close to the prediction interval, it's not really have meaningful insights, but definitely when you look at this, 91, 0.91 is a high correlation, and definitely there is a lot of information here. And now let's see how the correlation looks when you have seasonality. So we're going to apply it on the demand for natural gas. And now you can see how this series is correlated on the seasonal leg. So you can see there is high correlation with the first leg, but the highest correlation is with the seasonal leg 12. So this means that your point today, if we are here in September, is 2025 is highly correlated with September 2024, which is somewhere here. And also there is correlation going across the second seasonal leg, so leg 24 and 36 and so on, and it's decaying over time. And what I like to do when I'm using this plot is to mark the seasonal legs. So it's very clear when you're having a more uh, complex seasonality. Sometimes you have multiple seasonalities, like if you have hourly, it could be that the 24 is one seasonality in the day of the week. So I like to add this color and distinguish between the non-seasonal and the seasonal when it's applicable. For this, it's applicable. For the previous, when it's yearly, there is no seasonal component, so it's not applicable. But I found it very useful to see it this way when working with seasonal data. The other tools that we can use is LegSplot. And LegSplot is essentially as it sounds, you are plotting the series against its legs. Um, and I like to add the regression line just to see the goodness of fit. So in this case, I'm taking the number of customers, the first series that we saw above, and I am running a regression. So first I'm plotting the series against leg one, and you can see that's a very linear relationship. And also I am calculating a regression between the two, and you can see, just for indication, it doesn't mean that like it's not perfect relationship, or R squared doesn't really always tell us the full story, but it's give you indication how um, leg one expand the movement in our series. So that's a nice way also to visualize correlation by exploring the legs. And you can see as you're changing the legs, um, this variation is changing, and this is less linear. There is some curvature over here, and the relationship is not as perfect as the first leg. Uh, Likewise, you can see that this is the second series with the seasonality. There is some linear relationship with the first leg, but there is more higher relationship with the leg 12. So this is very aligned to what we saw over here, right, where the leg 12 is a stronger relationship. Um, and this is tell us just, hey, we can use this predictor. There is information, we should use it. So this is um, the correlation. I will um, go to the next topic unless there are any questions and talk about seasonality. And from there, we'll go and build our first forecasting model. So the next topic is the seasonal analysis. So we saw the demand for natural gas. The seasonality there is derived, usually the seasonality derived by the frequency of the series. Since it's a monthly, you should expect the monthly seasonality, but there are some cases you have more complex seasonality. For example, if you have hourly data or daily data, you may have multiple seasonality. One way to identify seasonality is by using seasonal plots. And so in this case that we have a monthly time series, a nice way to plot it is do a year over year. So now the way to think about it is you can see that in time series you have the cycle. There are two definitions to cycle in time series. One is the economical cycle, which is if you think about uh, when you look at GDP or any economical indicator, you have from when it's going up until it's going down. That's a full cycle. And when you're talking about time series, regular time series, when you refer to cycle, is in this case, for example, is a year, and the frequency of the series is the unit of the cycle. So here we are looking at the yearly data, and we're plotting a year over year. And what you can see, first you can see, for example, the growth. You want to see that over time, if your series is growing or is it overlapping, right? So you see some cases that it's below the previous year, so you should look at your growth. But also you see that the curvature is showing you the patterns of the seasonal component, right? So this is a simple way to look at seasonality. There are more complex plots when you have a multi-seasonality that you can apply. You can use a combination of a box plots and other methods that show you more or less the same. But the idea is to look at it over the cycle and see if you can see consistency in the patterns. So those are, in a nutshell, how we look at explore the data. There are, of course, other methods, but those are the basic ones that we will use in this workshop. So with that, let's go to the first notebook, and we'll start by modeling trend. And no, that's one. Okay. So now I'm going to do two things. I'm going to keep it open if we need to jump over here, but I'm going to use the R session and run the code. We build it step by step. So let's first do this. I will open R. Okay. And okay, I think we have everything that we need to for the setting. So we start with a trend, and generally the definition of trend in a nutshell is growth. Series is growing. There is a linear trend, which means that the series is growing on constant growth, and there is nonlinear growth. So, for example, exponential growth. The mathematical definition of a linear growth is the marginal change over movement of one unit. And why it's important, because when you think about in regression terms, you want to calculate what is the change when you are moving over one unit of time. So let's start by building this feature. So for this example, we load the same libraries. We load the data, and this file contain TS1 and TS2 that we're going to use today. This is the first series, the yearly, and this is the second series, which is the monthly. It's already reformatted into a table object, so it will be easy to work with. You don't need to do any reformatting, and you can see that it says index, and index in this case, table must have index. So one of the attributes of the table that you can check is regular. So you want to see if the time series is regular, and you can do TS2, and it's tell you true, and it's based on the attributes of the index. So if I do attribute TS1, you can see what are the intervals. In this case, it's a yearly. You can see what is the index field, and so on. So let's plot the data, and we already saw this, and you can see that it's fairly as a not perfect linear trend, but there's no seasonality. So we'll start with fitting a simple trend, and simple trend, the definition. Let's see if I can. Okay. Maybe I should go over here to go to the math. So the first model we're going to use is regressing the series against the index. And what is the index? It's any number that is moving in increment, constant increment. So in this case, we use index. We set indexes, a number that start from 1 all the way to n, which n is the number of observation. So if we want to generate this feature, uh, we're going to create this. And we are going to simply use the number, the corresponding number of rows as the index. And the mathematical intuition why we are using this to regress with the series is that this calculate the delta between when moving by 1 unit, the change in the series. Or in other words, this is the growth, the monthly growth. So if we apply the regression model, we're going to regress the y against the trend, and we're going to get this intercept and the trend. Now you can see that this is the value of the trend, and it's mean that every year the series is growing on average by 94,000 units. Right, that's the interpretation that you can use with this coefficient. One thing to see is that the coefficient are statistically significant, and we got a fairly high R square, adjusted R square. Now, if you do something different, for example, you can see that we created um, this trend, but you can use also the year. So the index, you will get a similar um, result. Summary. You can see that you got a similar coefficient, so the change from year to year stay the same. We just got a different intercept because we are now using a large number. But the idea is the same. It's increment by 1 from year to year, and that's how it's calculated, the trend. So you can use any number, any sequence of numbers. The only thing that will change is the intercept. And let's plot it the fit against the series, and we're going to repeat this process across the whole workshop. So this here I'm going to do it. I'm going to use the predict method. I'm going to feed the model that we trained, MP1, and I'm going to feed the new data as the actual data that we trained the data. And the intervals that I'm going to use is confidence. And so this is we use confidence when we are fitting the regression against the data. And if we are doing a prediction, we use prediction method. And then so once let's just run this. So you can see that it's create fit 1. And essentially it gives you a fit number and the lower and upper uh, intervals, the confidence intervals. And we're going to assign it to the TS1. So you can see now for each point we have the corresponding fit value. Okay. And the P1, we're going to plot it. So you can see that we got, because we just regress against one feature, so it's a linear line. And not the best fit, but we'll start with this and then we will go into fix it. You can see that that's the downside when you are using one feature, so it's capturing the average. So on average, it's give you this line, but the problem is that the series is changed. It doesn't capture changes in the series over time. So to understand the goodness of fit, we're going to use a method called residual analysis. And we want to measure some of the model assumptions and to see the goodness of fit. So go over here because it looks better on the process data. So we're going to use few plots. One is actual versus fit, which is this one. And this is give you like intuition how close the fitted value. And then we're going to calculate the residuals and apply SCF plot. What we want to measure if the residuals are white noise or no. Usually in time series, you will see that it's very common that there are patterns left and you see correlation. And this is the indication that we probably need to add more features. So this is really good test or visualization to see how the model is performing. And the next plot is residual distribution. And the reason that we measure distribution, we want to see the assumption about the normality of the residuals. And the main reason for that is that if the residuals are not normally distributed, the assumptions about the prediction intervals is the calculation won't be valid. So this is mainly if we want to use prediction intervals, we want to make sure that the residuals are normally distributed. So you can use a density plot or QQ plot. So let's go back and see how we can calculate. So the first thing we are going to do is, and maybe I should font make it a little bit bigger. So I'm going to calculate the difference between the series and the fit and call it the residuals, right? So that's the uh, re, re, a simple calculation, and I'm going to plot it. So overall, you can see that it's definitely not white noise. It has some wiggly shape and seems like there is some patterns. And we can add similar to what we did before with the decomposition method. We can calculate the standard deviations. And the idea, intuition here is that it helps you to understand where the model is doing really a bad job. For example, over here, right? And we can go and see why the model missed so badly this point where the model see the data. So maybe we need to build some additional features. And we want to check for correlation. So we're going to use the plot ACF function. And you can see that there are a nice significant amount of correlation left, mainly on leg one, which means that the model is not really capturing all the patterns that are available in the series. Last but not least, we will plot the distribution of the residuals, which is not too bad. It's fairly close to normal distributed. There are some tests, statistical tests, but usually it's nice to visualize it. This is the density function, and we can use QQ-plot. And QQ-plot is like in the regression that built-in plot function, right? So it's give you the quantile, the 4 quantile, and we want to see that it's close to this, that is really close to the diagonal line, which indicate that it's close to normal distributed. And again, like you see, this kind of like as we're getting to the tail, it's a little bit far from this line. So I took all those plot and created these plot residuals that give you all this information in a nicer way. So you can see it's nice to see all together. So this is the fitted value. This is the residuals. Note that something I like to do is to map the residuals um, that are outside the standard deviation threshold. So you can see this point is a big miss, and maybe we need to add here a feature. So it's really give you this information really fast and you understand exactly what's going on over here. And you can see together the correlation, the QQ plot, and the density. So we're going to use this plot method moving forward instead of creating it manually. So this is part of the functions that I mentioned before. So now we train the model. We want to generate forecast. Okay. So let's say that we want to forecast the next 5 years. Um, the first thing that we need to do, we just defined the forecast horizon as 5 years. Now we need to build the future data frame. So if you know the predict method, and let's go to the um, when you train a model and you want to predict a regression model, you need to provide the model and you need to provide new data with the features that we use to train the model. So we need to generate the future data frame. The nice thing about uh, the table that it's come with a function called new data that you provide your time series and then you provide the number of steps in the future that you want to generate, and it will generate this table with extending the index. In this case, it's a yearly, so you can see that it's extending to the next 5 years. So now on top of it, we can start to build the features. So if we're going back to the time series that we trained, the feature that we use is the trend. And you can see this is a continuous number that increment by 1. So what we want to do, you see the last data point of the trend is numbered as 38. So we want now to create a trend, and should be continuous. So the first point should be 39. So we're going to capture the last point, which is in this case 38, add 1, and then add it to this new table. And now we are ready. We have the exact features that we used, and we can now map it and use the predict method. So let's go ahead and calculate the predict. So we are feeding the model object. We are feeding the future data frame, this one. And now we're using, because it's a prediction, we're going to set it the intervals to prediction, and we're going to use 95% level. And then you can see that you get similar object with the fit, which is the forecast, and you have the lower and upper intervals. And now we want to assign it back to this future table. So we're going to use this code. So it's a metric. So if you want to map it, we take the first column is the fit, the second column is the lower and the upper. And so we're going to add it to the future table. And we're going to call the forecast as y hat, the lower and the upper for the lower and upper prediction intervals. So now we can plot the forecast. And you can see that this forecast is, it's continued the linear line, and it's really performing bad. So now we want to see how can we fix it. So there are a couple of methods that we can use. And the first, let's close all those plots. So there are a few methods. The first one, which I find very useful in this case, is piecewise linear trend, which is the ability to add nodes to the trend and essentially tell the model, hey, I think something happened over here. So I want you to segment the trend. Segment the trend from the beginning until here, and then create a new segment, capture the change in the trend, right? So that's essentially piecewise regression. And then you can use legs. So essentially, it's like a RIMA model. We're going to use AR process, which you're just going to regress the model with the legs. And part of the reason is that you can see that there are correlation with the leg one. So having AR model probably will reduce it. And you can combine both. So those are two simple. There are other mm, methods that you can use, but those are the one that we were going to focus. So let's build the feature. Let's start with piecewise linear trend. So if you eyeball the time series, you can see that somewhere over here, there is a structural break. And what we want to do is to create a knot at this point that essentially will generate one features that model the trend from the beginning, carry it to the future, and then new feature that start from here that will enable the regression to understand the change that happened over here in the trend. So to do so, we're going to use second feature. We call it trend two, which is going to, with the Pmax function, is going to be 0 up to um, 2008 and start a new a trend feature from this point, meaning it's going to be 1 for 2008, 2, 2009, and so on. And then we're going to regress it with the trend. So let's first calculate it. Let's just look how does it look in the data. So you can see that it's 0 um, all the way to 2008. Let's maybe expand it a little bit. It's refused to give me the, yes, let's do the view. And okay, so you can see that in 2009, it started to increment this feature every year by 1. Okay, and so now let's apply this with the regression and see how it's going to change the prediction. So we're going to call it model 2, and we're going to regress the series against the trend and the second trend feature. And you can see we got all the features are statistical, highly statistical significant, and let's plot the fit. And you can see now the model captured the change in the trend, and the fit now is much, much better. So if we plot it together, let's plot the feature together with the series to understand it better. How does it work? And you can see, so this is the regular trend, and we added the piecewise trend, which is 0 all the way to this point, 2008, and moving forward, it starts to increment by 1. And this is what gives us this fit to the series that is capturing this change in the trend. Um, I will link, there is a great uh, this one. This is a great article by Rob Inman that explain it's really simple method. Let me add it to the chat as a reference. Okay. So we can now go back and check the residuals, and we can see first the residuals looks a little bit better. We lost some of the normality of the series. You can see now that it's a little bit, look a little bit weird, but the fit is much, much better. Also, the correlation was reduced. Still some correlation, which just indications probably you want to add uh, AR1 process for this, like to regress the series against the leg one. And so there is some information left, but overall, this is a better forecast with respect to the previous one. So now we can update in a similar manner the future, because we had this feature, we want to add the future data frame with the new trend, and we can use now um, repeat the process. So before we did create the forecast by using the predict, then assign the fit value back to the object. Um, and I created a wrapper that do the whole process, and it's called LM forecast. So we just create it, and we can plot it with the plot LM forecast. And you can see now the the forecast seems much more reasonable or aligned with the reality than the one before. Now, of course, we are skipping a couple of steps. We didn't do like a out of sampling testing and so on. So that's something you should do. But our goal today is more focusing on how features impact the model. But you should take into account that you want to do some testing on the setting like a testing partition and evaluate the performance. Um, Before we move to the next topic, I want to show you this is a nice thing that you can build feature really fast. So I use Claude to generate some of these functions. So I created functions that look for the optimal um, grid, use some grid to find the optimal nodes. So what it does, it's under some assumptions, like you are setting a grid search of number of nodes, and it's look for what is the location. Let's say if you're saying I want a one node, so it's running a set of regression. It's moving the regression until it's find the best fit by using the BIC criteria. So let's see how does it work. In this case, I want to run piecewise, and I want to test up to three nodes, and I want that the segments will be eight, minimum of eight. The distance between each node will be eight observations. So let's run this function, and you can see that the optimal number of nodes is two based on this setting. Of course, if I will change the segment left, it might change. Um, but that's the optimal point. And now we can plot it and see like what is the suggestion where we want to put the nodes. So one node is in 1999, and the other node is 2007, which is very close to what we use on this node. We use 2008, but technically this is a more robust way to think about how to set those nodes, especially if you want to automate the process, is to run some algorithm that find uh, the optimal nodes. Think about if you have more than one series that you need to do hundreds of series, you cannot go and calculate it one by one. So this is probably you want to automate this process by using some similar algorithm to automate the feature creation. And we can simulate I was really playing with this function. So let's see if it will work. Oh, this one. So I found a library that enabled to animate this process. So it's creating now the search. It's record all the plots, and then we can see how does it's searching. So you can see that it starts with some point, moving it with one, then go to two, increment it, and then to three, right? And then it's looking for the one that minimized the BIC. So this is a fun visualization of this method. So let's move to AR. This is a very common method, autoregressor method, which is commonly used to, is part of the ARIMA. If you are familiar with the ARIMA, the AR in the ARIMA stand for autoregressive, and it's just simply saying we want to regress the series against the series legs. And so the idea is that we're going to use leg one or AR1 process. And to create these features, we're just going to use in dplyr leg functions to calculate the leg one. And you can see in the series that we added the leg one thing to know that when you add leg, you're going to lose some of the data points in your series, right? So in this case, we use leg one, so the first series we cannot. If you look at the Y, right? So this is going to be moved to leg one. So it's going to be over here, and this is going to be leg one of the third observation and so on. But for the first one, you won't have leg one. So if you are using, for example, leg 12, you're going to lose the first 12 observation. And when you're running a regression, you should take into account that the regression will omit those observations that have missing values. Okay, so but AR1 is very powerful in this case based on the ACF float, and let's go with it. And we're going to train a, a model, and you can see that when you're adding the leg one, it's very statistically significant, and now the trend feature is not as significant. And the reason that usually, in some cases, the AR process is enough to model the changes, and it's strong enough. Um, let's go and see the how it fits. And you can see it's um, similar fit to the like eyeballing this. I cannot see like a significant difference from the previous fit, but we can run the residuals and see if the correlation change. And you can see now that the correlation is really, or there is no any statistical significant correlation left. And the distribution of the error is now more close to normal. Right, so that's probably a better model. There's still like some anomalies here that maybe we want to add some feature. Maybe here you can see there is some kink in the series, but other than that, it looks very reasonable model. So now this is the catch when you want to forecast. Since we used leg, it means that we need to provide those legs to the future data frame. We use leg one, meaning that we can only provide the leg for the first observation of the future forecast. So this is the last observation of the actual, right? So if you go over here to the tail of the time series, you can see that this is the last observation, and we can use it for the future one as as leg one. But we don't have the observation to provide the leg one for the second and third and fourth and so on. So this is where we need to use a recursive method. So what we're going to do is first predict the forecast for the first observation. Once we calculate the forecast, we're going to um, assign it to the leg one as the leg one of the next observation and repeat the process. So this is computational a little bit more expensive because we cannot do in one go. We need to do it one by one. Um, but it's coming with a predictive power. So the trade-off is in favor of this method. So let's see how we're going to do it. So we first will add the available legs. So let's say if we use leg three, we could have the first three legs. Since we use only leg one, we can only populate the first one. And we're going to create the placeholders for the forecast. So if we're going now to create this, populate the forecast over here. So we're going to first predict the first observation. And we're going to use this prediction to populate the leg one of the next one. And from this point, we need a recursive function that keep doing it one by one, step by step. So this for loop, that's what it does. It's going from the first leg and increment each time, create the forecast for the next one, and populate the next leg. And you can see that, for example, this prediction was placed over here as the leg one, and the second prediction placed on the third leg one, and so on. And we can use this function already knows how to handle legs. So I add this like leg one as an argument, and it's generated, and we can plot it. And again, the focus looks really good compared to the first one. So this is the trend. I will pause here, see if there are any questions before we're going to go to the seasonal component. Okay. So let's just close all those plots. And I might open. So now we're going to focus on this time series. And we're going to see how to model the seasonality. So we will load the same libraries. We're going to load the same data sets. We're going to use now TS2. And you can see this series is already reformatted as T-Symbol object. It's a monthly intervals. This is the index. I'm also using a date object because um, the class of the index is monthly month year, which is a Symbol class for monthly data. But when you plot it, it's not really rendering well, and it's give like the numeric value of the index. So I also keep the date for the visualization. And this is the series. So we can start by already saw the series, and we can start by decomposition of the series. And you can see we are mapping the outlier. So remember those points. We're going to handle it later. But for now, what we want to address is the seasonality. We start again with adding trend. And once we have the trend, we will build the seasonality. So we do it step by step. And we saw already the ACF of this series. It's indicate of strong seasonality. This is very clear from the original plot. And we use the same method as before to add the trend. And we're going to model the trend. You can see because this is the only feature, you get this feature is significant, but now the R square is very low, which means that there's a lot of information that the trend doesn't really explain a lot of the variation in the series. So we can again plot it or use this function to plot the residuals, and you can see that um, that's a linear trend. What it does essentially, you see that the residuals is now the D trend of it's not it's out to see because it's not a line chart, but essentially it's detrending the series. And you get the seasonality left over here. And you can see that the seasonality in the residuals is very high. So now we're going to handle the seasonality. And creating features for the seasonality is straightforward. We're going to use the lubricate. So what we're going to do is to look at the index of this object is monthly. So essentially, we're going to create a categorical variable for um, each month that represent each month. And you can see now that we have the month, and we're going to use this feature. So one of the nice features in R with the LM functions that if you are using categorical variable, it's automatically doing the auto-encoding for this feature and apply it back to the regression. And so we're going to run the regression, and you can see that now we are getting those features that are representing the seasonal component. One thing to note with linear regression, when you have a categorical variable of 12, for example, in this case, it's 12 categories, each for 1 month, what the regression will do on the back end, it will remove one of the categorical variable, and it will be essentially part of the intercept. And so the reason for that is because when you're running a linear regression, because of the intercept, it's already backed into the intercept. So if you're building one auto-encoding by yourself, you should avoid having the same amount. The number of features should be n-1. So if you have a 12 categorical variable, you should have 11, and then the combination um, of the one that are neither one of those would be backed into the intercept. Where if you're using other regression models such as XGBoost, that's not the case. You're going to do 12 features. So that's a small distinguish between linear regression and other machine learning models. And now let's see the goodness of fit of this model. And you can see now we capture the seasonality. And again, that's going back to the myth that linear regression cannot get nonlinear relationship, and it's really capturing the curvature over here really good. There is some leftover information, but definitely it's not nothing you cannot handle with adding more features like legs, maybe a seasonal leg 12, leg 1. But overall, it seems like the model is valid. There is some leftover correlation, but it's normal distributed and seems reasonable. So now if you want to create the forecast, we're going to follow the exact same process. So let's say that we want to forecast the next 5 years, and since it's a monthly, we're going to create a forecast for the next 60 months. So let's set the horizon to 60. And now let's generate the future data. You can see this function, the new data will generate the index as a baseline. And now we need to add the features that we created. So we created the um, we created the trend, and we added the month. Let's see. Yeah. So we added to the new data the trend and the month. So those are the two features that we use with the regression. And now we can generate a prediction. And I left it this notice. One thing to know when you're using categorical variable is that you want to make sure that the number of levels on your future dataset align with the levels that you use on your training sets. Sometimes you have for example, when you're using leap year, you will see that some of the observations are are not available on your training sets, and you're trying to predict on a new data sets that has a new categorical variable or new level that was not introduced on the training, and it's going to fail. So make sure that you align your categorical variables with your training, what the model was trained with. This is mainly, you will meet it if you are using leap year features on, or like your leap year is on your testing partition or future partition. So let's create a forecast and let's plot it. And you can see that we created the forecast capturing the seasonality, capturing simple trend. Um, Probably it's not doing really well on those kind of like one of the things that regression does is averaging. So the seasonality that it's calculating, essentially it's a weighted average of the, if it's a January, so it's weighted average of all the Januaries and so on. We can handle it by adding more features. Um, but generally that's kind of like how to see it. It's average. So if you want to, if the you can apply some log transformation or some box cox transformation to make it a little bit more um, to normalize the series and capture better those variation. Um, one thing that a nice feature that you can apply in this case is structural breaks. So it's very hard to see here. Maybe if we go back to the decomposition, you can see there was a jump over here, right? And that's called structural break. It means something in a relatively short time, there was a shift in the series, either up or down. In this case, it's up, and we want to model this change. And one way to model it is by adding features that we're going to set it as 0 up to here and 1 from this point, and it will kind of like create a segment before and after this shift and apply it to the model. So let's see how that's going to work. So in this case, we're going to set the structural break starting from September 2018. So somewhere here. And so before it's going to be 0, and after it's going to be 1. So you can see this is the new feature, and it's 0 up to September 2018 and 1 forward. And if we model the series, you can see that again, we get that most of the features are statistically significant. One thing to mention about when you're using categorical variable, you can see that some features are statistically significant, some are not, and that's fine. As long as most of them are statistically significant, that should be sufficient, especially if you can see that there is a change between a model without or with this feature. But overall, you can see most of the features, the trend, the intercept, and the majority of the seasonal features are very highly statistically significant. And let's evaluate this model. And overall, you can see that the residuals are now much more central around the zero line. There are still like a point that we are missing, but it's improvement compared to the previous model. We didn't touch those um, correlation because the structural break won't really remove the correlation. This is we can solve by adding AR1 and AR12 processes. So if we want now to forecast the series, we need to add the structural break. So since we assuming that the structural break it's a one time, so we going to add keep it as one. One thing that you can do if you think that in the future you expect another structural break that is similar to the one that we set, so you can increment it to two and three and so on. Like if you have some step function, let's say that every year you have a sales events during the Christmas that create a structural break on your data. So this is a common method is by increment it every year to capture this level shift in this series. But in this case, we just keep it as one, and let's run the model. And you can see that now the trend is it's less trending up and more continue the trend with the most recent data point. So before we go into the last topic, which is probabilistic forecasting, let's talk about outliers. So we noticed before, if we go over here, there are some outliers. Also on the STL, if I will find this plot, there's so many plots over here. So you see, for example, here, there is an outlier. Um, and there are some other outliers, such as this point and so on. So we can now model those outlier. We can define magnitude. So you can have multiple outliers, and some are look similar and some are not. So we can define that, for example, this is you can see also over here a relatively high outliers, and we can define it as its own unique outlier. And other outlier, like for example, January 2014 and January, what else did I flagged over here? Over here as outlier and so on. We can define it as its own category. So we can define a high and medium. So a medium, this is going to be high and the rest going to be medium. And let's create the features for those. And you can see that maybe that's so you can see that we have here two new features, outlier high and outlier medium, and the corresponding values. And so they will be only at zero uh, all over, except for the point that we want to flag. And now we can update also the future table. And here again, this is we set it as zero, but let's say if you think that in the future those outliers going to appear for a variety of reasons, you can flag them in the future as one. And let's model this component. And you can see that again, those features also highly statistical significant. And let's for some reason it doesn't want to plot it, but uh, let's see what I did wrong over here. So there is some error here, but generally, um, it might be that I'm missing. Yeah. I assume that there might be some missing value that generating this error, but you get the gist of the this feature. With that, let's move to the last and the most fun topic, which is creating probabilistic forecast using the regression. So let's say maybe we're going to train the model again, the same model we just trained. And for some reason now it's working. But essentially, you can see after adding the outlier feature, it's um, it's now really capturing this. Also, here it's removed some of the outlier. The fact that you can still see some outliers mean that either we are still missing features, or they are with respect of the range of the residuals is getting shrink, and so you have now a new points that before were not considered as outlier, but now because we reduced the big outliers, so there are now minor outliers that are popping up. Um, but one thing that I want you to take away from this model is the coefficient, and that's a nice property of the linear regression. So if we do the summary function on the model, the regression returns the estimate, which is the mean of each coefficient, and the standard error, which means that we get a distribution. And we have a distribution. The fact that we are using the mean to calculate the forecast doesn't mean that that's going to be the actual value, because there is some distribution. And if you want to generate a probabilistic forecast, we can start to do sampling or simulation of different values using the distribution, the mean and the standard error, and calculate different paths. So if each time I'm randomly sample for each or one of those coefficient, uh, estimate of the coefficient from the distribution, apply it on the forecast with this sample, and then resample again. This is enable us to generate simulation and paths, and using this, it's essentially it's a probabilistic forecast. So I generate this function called sim forecast, which that what it does. It's drawing random sampling based on the for each coefficient based on this distribution. I can set the number of simulation. Let's say let's put it on 100. Hopefully, it won't be too big. And then we can plot it. So let's maybe zoom in. And one thing you see that the numbers here is because I use the index and it's not the date. Let's see if I will use the date, it will be showing the actual values. No. Let's zoom in and you can see there are different paths. Can I cancel this over? There are different paths, and if what the function is does on the backend is calculate for each data point the 50 percentile, the medium of the forecast. So if you can see here, this is the medium. The intervals are calculated based on the range of the distribution. And essentially, that's how any probabilistic forecast is conducted by calculate distributions of the observations. So that's a nice way to use a statistical model, the properties of the statistical model to generate a probabilistic forecast. And it's enable you to do simulation. So one other application is, let's say, about future events. So for example, we flag this as outlier, but we don't know if, let's say, it's derived from weather or cold winter, the consumption is increasing, what will be the weather next year? So we can say, oh, this is events with some distribution, and we can apply it also on the future as something that events with some distribution, and draw some sampling or a probability of this event will occur and run different scenarios. So this is very, very useful features to when you have some uncertainty and you want to model it with a probabilistic approach. And I will pause over here, see if there are any questions. We are almost on time, so I'm happy to answer any questions if there are over here.
Thank you, Rami. People, please don't be shy. If you have any comment or question, just unmute yourself and you can share any question, any thoughts or comments you have.
So I do have a question related to the events. For an example, COVID kind of like event. So do we, uh, as you mentioned, that we need to use piecewise linear trend in a way to capture those kind of event. Do we have any kind of other option to capture, or maybe to exclude or include those kind of events? Maybe uh, if we're supposed to include Russia and Ukraine, some kind of um, GDP of a country, or maybe uncertainty
Mhm.
nowadays we do have. So how are we going to tackle those things? I mean.
Yeah, it's a good question. I think there is more than one way to model specific events, right? So um, you can use piecewise in some cases. In other cases, you can, for example, what I showed the structural break, you can also use piecewise um, approach.
Mhm.
And COVID was the cases like when you saw a really abrupt change in a lot of time series. Um, in this case, you want to apply structural break. In other case, you want to use a feature that I didn't mention here today, but it's called spline. So, for example, if you know that you're going to have some event that's going to drive some spike and then decay,
Mhm.
you can apply some spline. If you know the beginning of the event, you can calculate kind of like the change derived by the event, and you can, if you don't know when it's going to end, you can make some assumption about the peak of this event in the future, and you are taking this spline and extend it, and then you can apply some decay factor that uh, that kind of like the spline from the peak is start to decay, and based on the um, you can set the level of decay if you want it to be faster or slower. And it's a very useful features for this type of uh, scenarios. So if you look at series from the COVID where public transportation that suddenly
Mhm.
there was no people stopped travel, and so you saw a drop, and then there was a recovery, and the
Yeah.
recovery was not at the same rate. This is
Yeah.
where public spline would be useful, because now we know how the recovery looked, but at the
Yeah.
point that people were during the recovery, you couldn't really know where it's going to go. Nobody knew
Yeah.
really. So this is where from business perspective, you can come and use the spline, extend the spline if you think that it's going to be a long recovery, or
Mm-hmm.
make it short for short recovery, and give scenarios. This is very useful when you're essentially you are manipulate the forecast because you don't know, but you are giving what if. So
Yeah.
spline is a very good feature.
And so that means for each of the event, we need to create a feature, and then we need to train on top of it. Maybe, and then we should use the lags compared to the original data, and then we need to keep adding those lags also while predicting it.
The lags are very useful when you see that you have a correlation left in the residuals, right? So if you see in this example, probably in this model, definitely you see that there is some lag 1 left in the residuals and lag 12. And
And
so
why
lags,
and why we're not capturing the lag 2 and lag 11 and lag 10 here?
because I didn't use it in the model, right? So I just want to focus on other features like how to handle outliers. But if you add these features, you will see
Mm-hmm.
that you it's just this plot just telling you, yeah, you left some money on the table, right? There are
Okay.
some information that left, and go get it, right? So you want to. This is like really screaming. Add add AR1 and
Okay.
AR12 to this model.
Mm-hmm. Okay. Got it. Thank you so much, Rami.
You're welcome.
Stephanie, you are on mute. Do you want to make a question, to ask a question? No pressure. I just that I saw you with unmute. Okay. You know, I'm a professor, so I can be quiet until my students react and not be uncomfortable with that. So I think we have something in the chat. Yeah, Hernan is asking if do you recommend any paper or particular textbook?
So Rob Inman textbook is the Bible. Let me find it really quick and put it in the chat. It's forecasting. Oh, usually jumping in my auto. I cannot find it now. In forecasting principle and practice. Let me put it in the chat. It's really there is a Python version, and the R is the original, but then there is also now a Python if people prefer Python. Really simple, down to earth book. And then there is also I think, I'm not sure if I linked it. I linked it let me put it again, about piecewise, really simple article, explains how does it work, the math behind of it. I would start with those, and there are the uh, trying to think about other books on time series. There are many other books that are also great, but they are more machine learning heavy. And there is a Nixla. It's a Python, but they have a great documentation, and they use a lot of the R functionality translated from R. And so the state of mind, if you are coming from R, it's very friendly, unlike other Pythonic framework for time series. So even if you are not using it, they have a good documentation that explains some of the methods. So I recommend checking those. Um, so I would definitely start with this book.
Good. We have another question from Francis. I will read so have this on the video for the people who will watch in the future. So, hello, Rami. Do you have any recommendation on what we can do if we have a lot of data at many different levels? For example, imagine you have a chain of retail stores and you have to forecast for each store and each product. Are there a specific strategy for performing the EDA and the subsequent forecast?
Yes. Cluster analysis for time series. There is another paper of Robinman about this. It's a really, I really adopt this method. So the idea is that if you have, for example, retail time series and you have thousands of time series, there are most likely groups of time series that are very alike. So let's say there are some group of products that they have the same patterns and other groups that are follow the same patterns because of seasonality and holidays and some foods are more available by seasons and so on. And so the idea is that you take all your time series and collapse it into for each time series into a row, that each row you are building features. And so let me put the package. It's time series features for Winman. Yeah, I'm Googling it. Oh, I found the article. And so the idea is that you are collapsing it into a unsupervised learning and you're applying cluster analysis with the principal component. So you are building a lot of features that capturing different um, characteristics, and you try to find the relationship by applying some k-means cluster or together with the dimension reductions like PCA and put it together, and you're trying to say, oh, this group, very similar. Let's take some of those series and understand why they all look the same, apply some models, and then expand it to the rest and see if it's working. And so instead of like going one by one, a lot of the stuff that I showed today, it's very tedious to apply it, right? So you cannot go and check correlation for each series and uh, run the same residual analysis and right. Um, but once you understand the concept, you can apply it at scale by using those methods. So that's one method I recommend, and I put the article with example. It's very simple and intuitive.